Hello, I'm Jian. Today I will talk about our paper, Vulnerability-Oriented Testing for RESTful APIs. Nowadays, RESTful API has been widely used. For example, you can see it in cloud services, CMIs, and IoT. However, more and more security issues are appearing on APIs. For example, there was a photo API bug in Facebook, which may have affected millions of users. So, we want to ask, how to discover API security weaknesses to make your API more secure. Let's start by looking at existing methods, using RESTful as an example. RESTful is a popular tool for testing APIs. It creates complex test cases and can find issues like server errors, resource leaks, and hierarchy problems. However, it's not good at finding specific security problems like SSRF and cross-site scripting. Also, it takes a lot of time to test the application. So, what should we do? Let's think like a hacker. Imagine you are an experienced hacker. You want to test SSRF in Jellyfin. But there are hundreds of API endpoints in Jellyfin. You want to test as fast as possible. So, our problem is, which API endpoint should be your primary target? Assume you have a application documentation for Jellyfin with so many endpoints. Let's say image is remote. The documentation tells you it is for getting a remote image. And you notice there is a parameter named image URL. You may think, what if the image URL points to an internal resource? So, you target images remote, sending a request with image URL set to a typical SSRF payload. The server then requests the internal service, receives a response, and sends it back to you. This is how you successfully discover a SSRF vulnerability in Jellyfin. Why did we choose this API? Intuitively, there is a distinct connection between specific API security vulnerabilities and their functions. For example, SSRF bugs often appear in API endpoints that request remote resources, where unrestricted file upload vulnerabilities are related to file operations. But how to verify this? We analyzed the 6 CVE types. We manually summarized the functions of APIs corresponding to each bug, if detailed API information was available. We derived the insights from API documentations, source code, and detailed vulnerability descriptions. Let's take this CVE as an example. We know the vulnerable API endpoint is API JSON from description. By checking the specification, we understand it is for loading a file based on a URL. The result shows that SSRF is prevalent in APIs that request remote resource. Example keywords include remote, proxy, and URL. The hit rate is about 81%. Other vulnerabilities also have similar patterns. On average, 57% of vulnerable API interfaces affected by a specific type of bug belong to the same functionality. So, how can we integrate our idea to develop a new testing method? We face three main challenges. First, how can we efficiently identify API functions and find potentially vulnerable ones? Second, how can we create test sequences that match protocol states and target vulnerable interfaces? And how can we generate valid test cases for different functions based on their security vulnerabilities? This is architecture of our tool, VO API. We start by passing the API specification. This helps us understand the structure and functionality of the APIs. The passed data is sent to the function vulnerability mapper. This mapper is built using path keywords and parameter keywords from the CVE database and expert analysis. This process identifies potential candidate APIs that might be vulnerable. We then use the test sequence generator to create valid request sequences. This involves constructing the first sequences and generating parameter values. The test case generator produces specific test cases. The test cases are sent to the vulnerability verifier, which communicates with the API application. The verifier receives the responses and, based on the feedback, determines if the API is vulnerable. If a vulnerable API is found, we generate a POC. In semantic keyword collection, we analyze CVEs and NVDs to conduct word frequency analysis and use expert experiences to identify keywords. This keyword helps us get the function of API endpoints. Next, we focus on candidate interface extraction. In this module, we pass the API specification and use path and parameter keywords to deduce the function of APIs and map potential vulnerability types. Let's see how reverse sequence construction works. First, assume there is an API endpoint with two consumers, collection ID and document ID. We identify potential producers. Notice that the first and the second producer share the same path. But in our rules, post has higher priority than get, so the first one is removed. To summarize, we use producer-consumer relationships, crude semantics, and resource hierarchy to identify producers. To test for bugs in API endpoints, we use the test case sender and the validation server. The test case sender sends requests with payload and the API application response. If there is a bug, the validation server provides feedback to the test case sender. For example, if there is a SSF vulnerability in the API endpoint, the validation server will receive a request from the API application, feedback to the test case sender, then generate a POC. There are some samples in our testing corpus. We use different corpora for different API types. To evaluate, we ask three questions. Can VO API discover vulnerabilities in real-world APIs? Can VO API efficiently generate test cases? And how does the vulnerability-oriented strategy of VO API affect the testing results? Our dataset includes 7 real-world RESTful API applications of 3 scales. We chose 5 tools to compare. CAP and Astra are vulnerability or scanners, while the others are RESTful API testing tools. This is basic result for question 1. VO API found all vulnerabilities, while other tools identified only a few. Notably, our tool identified 26 vulnerabilities, 7 of which were previously unknown. Out of these, 23 have been assigned CVE numbers. Other tools could only detect a few vulnerabilities. To answer question 2, we extracted the testing sequence generator module of VO API and compared its coverage to other API testing tools. We found that VO API achieves comparable results in coverage. Lastly, we removed the vulnerability-oriented strategy in VO API-V. No new vulnerabilities were found by VO API-V, and it was much slower. This proves that our vulnerability-oriented strategy is effective. To summarize, we propose Field API, a novel inspection framework, to apply a vulnerability-oriented strategy to inspect bugs. Based on the insights that the type of vulnerability hidden in the API is closely related to its function. Field API found 7 zero-day and 19 disclosed bugs on 7 real-world RESTful APIs, and we publish our code in this report. Thank you for your attention. I'm happy to take any questions.